This question gives us a function, wants us to differentiate it, use derivatives to find increasing, decreasing, maxes and mins. All right, so it says take the derivative. Let's do it. So come on down. S prime, the derivative. Now, how are we going to do that? That's the product rule, isn't it? Product rule. Because it's two functions multiplied. So they take turns. Root of the first one, 1 times the second one, unchanged, plus the first one unchanged is not his turn, times the derivative of the second one. And how do you do the second one? Well, I'm going to make that a zero point 0.5 power because that's what a root is, a zero point 0.5 power. So I'm going to bring down the zero point 0.5, right? And then subtract 1 from it, it'll be negative zero point 0.5 times the derivative of the inside. The chain rule says if the inside is anything other simple x, the derivative of the inside should be negative 1 because the derivative of that negative x, right? The 1 comes down. So negative 1, the 3 is just 0. So there we go. That's a tricky derivative. Easy to mess that up. Be careful. So this is ugly. Oh, and what are we going to do now? We're going to set this equal to 0. Why? Why am I saying equal to 0? Because that's how you find the critical values. Why? Because the derivative, remember, equal to 0, that means the slope. Derivative is slope. So think about it. If you have a graph, you want to know the high points and the low points. At the high points, at the maximums, if you're on a roller coaster, you're flat. For just a second, the very tip top, you're flat. You're horizontal. Your slope is 0. Your first derivative is 0. Same thing at the bottom. For just a second at the bottom, you're 0. And in between, you're increasing or you're decreasing, you're increasing again, right? But those places where the derivative is 0, the slope is 0, those are critical. They tell us the maxes and the mins, and in between those is increasing, decreasing. So I got to take the derivative and set it equal to 0. Find out what will make this whole mess equal to 0. Now, this is not easy. Let me help with this. So I'm going to suggest you make this 3 minus x to the zero point 0.5 minus, what I'm going to do is I'm going to put these numbers here. This is a point, didn't do that so well. This is a zero point 0.5 here. So I'm going to multiply x times zero point 0.5 times negative 1. That's negative zero point 0.5x, just to keep it simple, right? Just put those together. And then we have 3 minus x to the minus zero point 0.5 equals 0. What are we going to do with that? Well, here's how you want to look at so important in calculus, these higher math courses, that you look at these things correctly. This guy's the separator. Pluses and minuses outside of parentheses separate things. So what? So that means you should look at this guy's one term and this guy is another. That's how you should be looking at it. This guy's the separator. Okay, so what? Well, what do they have in common? What do they both share? They both have that 3 minus x. Now, one of them has a zero point 0.5 power, the other has a negative zero point 0.5. Which one do you put outside? Always the lower one. Always. So we factor out the lower power of whatever's in common. So whatever's in common, it's called the greatest common factor. You take out the lower power. So it's the greatest amount they have in common. So, all right. And then what I'm going to do brackets. You don't have to. I wonder if I do that. Yeah, nice. And here. Um, Again, you don't have to, but I think it'll make your life easier. Okay, what goes on the inside? This times, how are you going to get back to zero point 0.5? It's 3 minus x to the positive 1. Do you realize that? When this multiplies that, the powers will add. 1 take away zero point 0.5 will be positive zero point 0.5. You see in that? I know that's not easy. So when this multiplies this, when two of the same thing multiply, the powers add and subtract. So 1 take away zero point 0.5 will go back to positive zero point 0.5. This is a positive zero point 0.5 here, right? Minus, and this will just be the 0.5x, right? Because that way, when this goes there, it will indeed go back to this. Because you've already got the right power. 3 minus x to minus 0.5 times this will go right back to that. Do you see that? Okay. So now where we go from there? So that's a tricky step, which is I learned when I was taking calculus. Okay. So minus 0.5. I did brackets. I just did that so it looked different than parentheses, but you don't have to. So, okay. And then now in here, 1 power, that doesn't do anything. 3 minus x minus 0.5x, right? See what I'm doing there? Oops. Not so good. Oh boy, I better be more careful. Here we go. Equals 0. I just write that 1 power really wasn't doing anything, so I just got rid of anything to the 1 power is just itself. Now I can combine this. This is minus 1x and minus 0.5x. So then I've got, and I'm just going to make this parentheses, same thing. 3 minus 1.5x equals 0. Right? Minus 1 and minus 0.5. If you lose $1 and lose 50 cents, you lost $1.50, right? Okay. Okay, we're getting close. So we're trying to solve this equation. How are we going to do it? Well, we want to find anything that'll make this 0 or yeah. So okay, 0 or um, yeah, let's just leave it at that. So okay, so I want to set each part equal to 0. So yeah, let me show you. This is negative power, right? So he's going to go back down. Yeah, let me do it that way. Probably easier for you. Right? That this will go back down. It'll be 3 minus x to the positive 0.5. Remember that? Remember how negative powers go down and then they become positive? So you got to know that negative powers aren't happy where they're at. They want to go to the bottom of the fraction, then they become positive. Okay, a lot of rules to know. All right, so now how's that going to equal 0? How's that going to happen? Well, we really are interested in anything that'll make the top or the bottom 0. So because if you make the bottom 0, that's undefined. If you make the top 0, that's 0. So if you make, you know what I mean? If you have the top of a fraction, 0 like 0/3, that's 0. If you have the bottom 0, that's infinity. And really, we care about infinity or 0 because they're both critical values. Critical values are anywhere where the derivative is 0 or infinity. So whatever makes the top 0, so I'm going to take the top over here. I'm going to take the top, the numerator, and I'm going to set it equal to 0. And I'm going to take the denominator and all by its own self to the positive 0.5 and set it equals 0. Anything that makes top or the bottom 0 is 0 or infinity. So that's 3 equals positive 1.5x divided by 1.5. X is 2. How about here? What are you going to do with that 0.5? How you get it? Well, that's a square root rule. Let's go by square root. So how are you going to get rid of that square root? Second power both sides, huh? And the second power cancels the root. So 3 minus x is 0 squared is 0. Jump the x over. X is 3. So we got our two answers. X is 2 and x is 3. Now, I'm actually going to chuck the x equals 3. Bye-bye. Why? Because if you look back to the original function, if you put in a 3, oh, no, he's okay. Yeah. Do you realize you can't go past 3? How about that? If you go like even 3.1, then the inside of that root's negative and it's imaginary. So you can't go past 3. 3 is a stopping point, right? 3 is a stopping point for that function. So that's why, yeah, he's not really that. I mean, he's kind of important, whatever. All right, let's go to the number line. So now to find out what's going on, we got to go to the number line. And I'm going to put these values on the number line. I'm going to put 2, and then I'll put 3 because 3 is the end. Remember, we proved already you can't go past 3, you get imaginary numbers. So I'm going to check in between those. So I'm going to check somewhere over here like 1, because and then check in between somewhere like 2.5, 2.5 or whatever. Right, I'm checking. So 2 is critical, 3 is kind of critical. I'm going to check in between and in between. I mean, 3 is critical, but it's also an endpoint. So check in between, check in between. So I'm going to find out what is that function doing in between. So boom and boom. So here we go. Now check what? Check the derivative. Let's go back to where we first took the derivative. Um, yeah, I mean, it's a mess, huh? How about we just use this one? Or we could do the factored one. Whatever, let's use that one. Well, um, yeah, whatever. They're all good. Um, I'll just use that one. So it's kind of a pain, isn't it? Yeah, it is. You could use that one, or you could use the cleaned up. How about that? How about right here? Here, let's use this one. That's more clear. That's still the first derivative, right? And it's just cleaned up. Let's use that. 3 minus 1.5x. So I'm going to go f prime is 3 minus 1.5x over 3 minus 1.5x over 3 minus x to the 0.5. 0.5, yeah. And I'm going to check what? I'm going to check 1. I'm going to plug a 1 in there. I'm going to plug a 1 in there. All right, so I'm going to go to Desmos now. 3 minus 1.5x over 3 minus x to the 0.5. And I'm going to plug in the 1. So I want to check what's happening. So here we go. Going to Desmos. And I'm going to do a fraction button on the top. 3 minus 1.5 parenthesis. What am I plugging in? 1. It's my checkpoint. On the bottom, parenthesis, 3 minus, again, I'm plugging in 1, parenthesis, to the power 0.5. Huh? There it is. I got 1.06. So f prime is 1.06. Namely, most importantly, it's positive. So that's the slope is up. The graph is going up in that section because the slope's positive. Now let's check 2.5. So what's f prime? I'm going to go back. I'm going to plug in 2.5 now to the same function. I'm still plugging into 3 minus 1.5x over 3 minus x to the 0.5 because that's the derivative. But I'm going to plug in the 2.5 now. So let's go back, make that 1 become 2.5. 2.5. Oh, come on. 2.5. Make that 1 become 2.5. What do I get? Negative 1.06. Notice it's negative. So prime is negative 1.6. So that's the slope. And so the slope is negative. So then the graph is going down in that section. So now we know about the graph. What? The graph is going up, and then the graph is going down, and we know the graph stops right there. So it's going up in the first section, down in the second. What does that tell us? That tells us this is a local max. 2 is a local max, and 3, it just stops. So now you might say, well, that's a min. Well, we don't know because over here it could go lower, and you say, well, this is local. No, we don't. You're only local if on both sides it's if it came back up on the other side, then it would be lower than both sides. But it just stops. It doesn't go to the right because that would be imaginary values. Remember back in the original function. So this is neither a local max nor a local min. It just stops there. But that's a local max. And so we can answer our questions now. Okay, where's it increasing? Actually, that's the first question. Where is this function increasing? Well, now we can see what's happening. This is going from negative infinity. That's a terrible infinity, huh? Negative infinity, this is 2, this is 3. So it's increasing from negative infinity to 2, and it's decreasing from 2 to 3. Huh? So it's increasing from negative infinity to 2. It's decreasing. You could put either way, 2 to 3 or 2 with a bracket, whatever. Where is the max? That's at 2. We proved that. Two's the max. Okay. And then where is there a min? At D and E, it does not exist. Again, this is not a min because it doesn't, you have to be a min, you have to come back up on the other side. It doesn't do that. So it's neither. So that's D and E. And finally, let me just show you. I graphed the original function on Desmos. There it is. It is increasing all the way until 2. 2, you see, is the max. It's a local max, and then it stops at 3. Just like we said. It's increasing to 2. Oops, I need to do that. It's increasing to 2. It comes down to 3. We did it a little more dramatically. It's increasing to 2, then comes down to 3. So we got it right by using derivatives. Derivatives are powerful. Tell us what a function's doing. And there we go.